Welcome to the second lecture on the module on VLSI testing. So, in the last two lectures basically we tried to give you an overview of digital testing, automatic test pattern generation, scan chains etc., which is actually prerequisite to understand the optimization techniques for testing which is applicable for circuits of higher complexity like NOC and SOCs. So, basically as we are throughout discussing in the course that basically we are first covering the basic principles of digital design which are applicable for slightly mediocre level of VLSI circuits, and then we are moving into some of the techniques which are required for modern day complex circuits. So, in that series on testing now we will be starting with optimization techniques for automatic test pattern generation. So, as already discussed, optimization in the context of this course is to look at the aspects which are required for modern day complex circuits which cover systems of systems like system on chip, NOCs, multiple cores on a single die, something like that. So, basically if you see what are the steps for automatic test pattern generation optimization. So, one of the basic default idea will be to speed up the ATPG approach. So, as we have already discussed in the last two preliminary lectures that test patterns can be generated by two methods. One is the test fault simulation method, in which case we give a pattern, a random pattern, and try to see how many faults get covered. By that method basically we cover up all the easy faults, and then we go for basically testing of so called difficult to test faults by sensitize, propagate and justify approach, which is a deterministic approach. So, basically that is where optimization is required, but that is not exactly a part which is to be covered in advanced test cases for advanced circuits. Basically for even for smaller or medium scale circuits we have to go for optimization at that level. So, we will be just covering this part in a very brief manner, and then we will try to cover the other aspects of automatic test pattern generation or test optimization, like generation of quality test patterns which can cover different type of advanced faults which are more relevant towards the technology which is relevant for modern day VLSI fabrication. Then we look at techniques to compress this test pattern so that we can have a smaller test set or a compressed test set which can lead to better optimal results. Then we will also look at some kind of some concepts of like test at the abstract level. So, that means as we have already discussed that if you are going at the gate level, the things will be too complex and too elaborate, or basically in other words test will be too complex, or we have to go to very granularity level. So, we have to do at higher levels of abstraction like at the register transfer level, even the fault models has to be at a very abstract level and so forth. So, basically our main coverage in this not only in today's lectures, I mean including today's and the next few lectures on this module will be mainly covering trying to look at these aspects, that is good quality test patterns so that it becomes relevant to modern fault models, how to compress tests and go for an abstraction level. But just before we touch, we will just see what people also have tried of different kind of optimization which is again relevant towards the traditional circuits, that is how we can go for a better sensitized test pattern generation by sensitize, propagate and justify approach. Just before I start this, I will just try to highlight one important point. There are two parts in testing. One is test pattern generation, which is actually a one time activity. You take a circuit and then try to find out what are the patterns, and then if the circuit is very large you may take days and months to find out test patterns, but still that is okay because you are going to do it just for a one time. And second is basically the test patterns which has to be applied to the circuits which has to be done for all the samples, because we know that yield is not too high, so is not as high as 99% plus, so you have to test each and every sample. So, at that point the number of test patterns to be applied should also be less. That if you have a large number of test patterns and as all the test patterns has to be practically applied in all the circuits, so the number of test patterns required to do the testing should also be brought down. So, that is a more important aspect than reducing the time to generate the test patterns. So, that is why we actually call quality of test patterns, that is we should have very good quality test patterns so that you can do testing more effectively with a less number of test patterns. So, this is more important than corresponding to speed up the algorithm to determine the test patterns. Nevertheless, that is also an important aspect, because if you have a very large circuit you may land up in years to generate the test patterns. Okay. So, as already discussed, nobody can go for functional testing because that will actually make the things very complex and you may not get a solution in years. So, you always go for fault models. So, what is a fault model? Fault model basically you assume that there is certain kind of faults that may typically appear in the circuit and you have to validate that those faults are not there. So, fault model is basically an abstraction of the real defects. That is, if you go for transistor level testing, if you go for physical means layout or such kind of testing of this testing of the devices at the fabrication level, like testing of the vias, testing of the interconnects, that may blow up the thing, blow up all the algorithms and the time required to do the testing, and it is also not required because it has been found out that if you have really good quality test fault models, then basically the second point should hold, that if one verifies that there are no faults of the model in the circuit, then the quality of test solutions is maintained. That is, the correlation with real functional test or the real so called the most accurate way of testing, like you test at the most rigorous level. So even if you can have such good kind of fault models which can tell that if no such fault model is there, then you can be 99 point plus sure, or the correlation level is so high that if you are assured that no fault on the fault list is in the circuit, then you can be very assured that the circuit does not have any kind of real defect. So we require good kind of fault model. So that is the de facto standard which you are always applying. Again, we discussed that the single Stuckat fault model is one of the most widely accepted fault model, because till last 10 years back, if you could verify that there is no single Stuckat fault, the circuit can be considered to be having no faults, and the correlation was also very high. So what was the Stuckat fault model? You assume that each of the lines of a circuit can be either Stuckat 0 or Stuckat 1, and you have to verify that by test pattern application that none of them occurs. And generally you call it the single Stuckat fault model because you consider only one line at a time. And that was actually one of the most de facto applied test pattern. So this is the first fault model on which every application or test for almost every circuit was based on. So now I will just give you a very brief idea that how people thought of optimization at that level. So given this fault model, how people tried to optimize. The first part is basically in sensitize, propagate and justify approach, is that you have to sensitize, like this example already we have discussed. We have taken a Stuckat fault over here. Let me zoom this. Just I am not going to elaborate because already we had discussed this example. Then what we have to do, you have to sensitize the fault, Stuckat 0 fault, so you have to apply a 1. Then you have to find out one path where you will propagate the value to the output. Like in this case we had selected E, F, G and H, and then actually the D will propagate, and then you have to justify. So then if you just look at this part, we tried to justify this approach, then actually it is D prime, so you have to apply a 1 over here, we require a D at the output of an OR gate, so you require a D of 0 over here. But if you look at it, if it is a Stuckat 0, we apply a 1 D, and then basically the output J cannot be a 0, because to get a 0 we require 1 and a 1. So there is a conflict. So what actually it says, that lot of works have been done, you can find out in the references which will be uploaded in the course site, that lot of first level optimization which people thought on ATPG from the classical level of circuits, is that how can we find out good path for propagation and justification. Like for example, we have found out, we have taken this path which actually failed and there was a conflict. But now we had already seen in the last class that if you take the other path, like same thing as sensitize by applying a 1, but now I am using the path I, J, G and H. So in this path basically you can see D inversion, D prime, D means normal 1, false 0, so it will come out through this path, and then if you have to, this is an AND gate, so justification D should be equal to 1, and this is OR gate, so it should be 0, and you can easily make F equal to 0 by applying A equal to 0. So basically what I want to say is that the second path basically, this is a good path for propagation, and then you can get the solution. So first level of optimizations that people try to think is to find out good quality test paths for propagation, because in this case there are only 2 paths, but in a real circuit you will have hundreds of options. So which option to try? So a lot of work has been developed to find this such kind of good paths, and lot of work has been done so that you can speed up the test pattern generation algorithm. In this course, as we will be mainly looking at the circuits which are beyond the simple typical VLSI circuits, so we will not go into depth of such algorithms. You can read lot of such papers because they are more than around 10 to 15 years or even 20 years outdated. But still whatever VLSI test algorithms are still running in picture, always try to find out which are the typical good candidate paths, because if you are taking a wrong path basically, then you may have to keep on iterating. Second very interesting part is something called redundant faults. Redundant faults are such faults which cannot be tested because there does not exist any pattern which can test it. But then how do you know? Because you will have a fault, like in this case, you have a fault and you have multiple paths for propagation and justification. So, what is a redundant fault? Redundant fault is a fault which cannot be tested. There does not exist any pattern which can test it. But how do you know that? You will be able to find out only by applying the exhaustive enumeration of all the paths through which it can be propagated, and then you find out that they cannot be justified. So, if there are, like for example in this case, maybe there are 100 fan outs from this, all the paths you have to try, then only you will be able to find out that there does not exist any pattern to test it, and then you know that this fault can be tested. But it is a huge waste of test computation resource time, because you will be trying so many paths and in the end you will find out that there is no pattern to test it. So, another important optimization principle which people try to find out is how basically you can find out redundant faults, that without trying for an ATPG approach. So, just let me give you an example, so you can easily appreciate the fact. So, this is a circuit with a simple Stuckat 0. So, if it is a Stuckat 0, of course, you have to apply a 1. So, you have to have a sensitization of 1 over here. So, normal 0, fault 1, D prime, and of course, there is only one path to the output. So, you output as a D prime at E. Now, of course, it is a OR gate, so you require a D over here. To get a D over here, of course, you require a 0 over here. But in fact, you see, but to get a 1 at this output of this AND gate, you require a 0 and a 0. So, there is basically a conflict. So, simple conflict in this case, and you know that this fault cannot be tested, as simple as that, because there is only one path through which can be outputted. So, there is no other option to try. So, just by one iteration you can find out there does not exist any pattern to test it, because there does not exist any other path for propagation, because the path we have taken for propagation there was a conflict. But if I told you, so this is an example of a redundant fault, the fault which cannot be tested. But if there would have been many fan outs, then actually would have been a real soup, because you have to try so many paths. Maybe I am assuming that there was no other path from which the fault could be successfully propagated and justified. I am having that assumption, but then only after so many huge number of iterations you would have been able to conclude that. Not a good way of handling. So, basically now people try to find out why such things appear. So, people have found out that such things appear because this circuit is actually redundant. This circuit is not optimal. If you look at this, the binary expression for this circuit is A plus B, A dot B, and basically you have plus, sorry, it is A dot B plus B, correct. So, this is A dot B and this is A dot B plus B. So, you can easily reduce it to the form like A B plus B. So, this is what is the expression, that is equivalent to B into A plus 1. So, A plus 1 is nothing but 1, and then basically is nothing but 1. So, the whole expression is nothing but a simple straight line. So, that means what? This is a redundant circuit. That means the circuit has not been properly, sorry, this circuit A plus 1 is 1, then the circuit is actually B. So, this is basically nothing but the gate B. So, this is simple line, the output E is equal to B, just a straight line, straight wire where B is connected to the output. So, that means what? This circuit is not an optimized circuit. You have put lot of redundant gates. So, in VLSI design, sometimes lot of redundancies are put to avoid hazards and put buffering arrangements, etc. Generally, to avoid hazards, people would sometimes put redundant gates. But then somebody should identify the redundant circuits beforehand, because if you go for a real optimal VLSI design, which has already been covered by Chandan sir in the case of design, that generally do not try to give any kind of redundant circuits, because they will unnecessarily not do any job, but will eat up your area overhead. But so such cases, generally we keep it for a very explicit purpose, because no automation tools or design tool will give you a redundant circuit. Just in this case, because if you optimize this by any standard technique like espresso, Carnot map, Quinn-Maclensky, you will going to get the solution E equal to B. But then why this explicit circuit has been kept? Sometimes people keep to avoid hazards. You can look at any standard digital design or VLSI design textbook. So to avoid hazards, people try to maintain such kind of redundancies. So, in such case, redundancy should be explicitly told to the test engineer, so that you should avoid such kind of faults in those parts of the circuit, because they are generally untestable. So, if there is a redundant fault, that will actually take lot of your test computation time, because you will be unnecessarily keep on finding out the loops. But these two aspects mainly, that is how to find out good test paths for propagation and how to find out redundant faults and eliminating them, are basically the first ideas of optimization which people tried on classical VLSI circuits. Now, we will be coming to the real part of our course on optimization of test. So, the first part which needs to be applicable to modern SOCs and OCs is to advance the fault models. Because as of you might be thinking that Stuckat fault model is a very simple fault model. You assume that all the lines have a stack 0 or stack 1, and you have to find out by test patterns that none of them exist, and then the correlation is 99.9%. So one question all of you might be having is that is really such a simple fault model going to accurately match my functional results in a very deep submicron technology? The answer is no. When Stuckat fault model was a very nice model and very highly accurate model, actually when we were actually talking about that phase of time when Stuckat fault model was a de facto standard and you could get very good results, the micron was around 5 micron or more, or it was not very deep submicron at that level, it was some 5 microns or higher than that. So in that case what happens? The higher the micron technology, the more is the gap between the two lines which will be laid out in the VLSI circuits. So in such case, as the gap in between the two lines are high, so the probability of faults occurring there will be lower, or in fact if even the faults were there, they generally led to something like these lines being cut, that is a Stuckat 0, or sometimes something used to happen is due to interference etc. So this line will always be Stuckat 1. So generally other than that more complex level of faults were very rare. So Stuckat fault models somehow intuitively or statistically they gave very good results. But now in deep submicron technology, and also at that time the frequency was also less, not in the level of gigahertz, so interference etc. were quite less compared to the modern day deep submicron technology. In deep submicron what happens, in 45 nanometers etc., the line being laid are so near to each other that sometimes there is a short in between these two lines. That is, the lines gets coupled, or there is a lot of interference leading to something called more advanced type of faults which occur. There is something called a bridging fault model. In fact, it's a fault, again bridging is a fault model. Basically these two typically lines, in bridging what we assume that the two lines have got stuck, and then you have to try to find out that such faults does not occur in the circuit or is not present in the circuit. For that we have to find out test patterns. But again, as it is a fault model, always you cannot assume that this nicely two lines will be stuck and you are going to get a short, and that is the real fault which you have to validate. Real defects can be extremely different. It may be happening something like that n number of lines might have got stuck at a point. Or it may be like that the lines have not exactly stuck, but there are a lot of electromagnetic interference, in which case these signals are getting coupled and value of one signal is dominating over the others and vice versa. So in fact, but the motivation is that in case of bridging faults, you take two or more lines at a time. In Stuckat you take only one line at a time, and in case of bridging fault you take multiple lines to be coupled in a fault. And that is more relevant because when deep submicron technology started coming into picture, people were finding out that the correlation of Stuckat fault is going down to even 70% or less. That is, you are having test patterns and you are trying to find out faults, but the problem what was happening is that the correlation is 70% or even less, because as I told you, in deep submicron the lines are coming nearer to each other, so you have to consider such kind of fault model in which multiple lines are considered into the modeling factor. So the first modeling technique which is applicable to advanced circuits is a bridging fault model. So as I have told, majority of Stuckat faults are considered, but in modern integration technology single Stuckat fault model can capture only a small fraction of real defects. That is why the correlation is coming down. So advanced fault models like bridging fault, transition fault, delay faults are actually now being adopted. So in today's lecture basically we will try to see how this modern fault model, what are these modern fault models, and how basically you can go for ATPG of these faults, and then very interestingly we will find out that if you are covering the advanced fault models, automatically Stuckat fault models are getting covered. That is, Stuckat fault models sit a smaller set, these advanced fault models are the bigger set. So if you are studying for Stuckat faults, you are actually leaving some outer space, but for the advanced faults if you cover, all other things are basically getting covered. So those philosophies we will try to develop. So one of the first such type of advanced fault model is basically the bridging fault model. So what they assume that any two lines in the circuit under test, that is the cut may get stuck or may get coupled, and then you have to find out whether they exist or not. But again, this is again an optimization. So one thing I just forgot to tell you, optimization basically I have told you that there are two types of optimization. One is the reduction in the number of test patterns, and one is the reduction in the test pattern generation time. But there is another factor actually, whether you are going to do the optimization at the cost of some quality of service, or your optimization does not involve any quality of cost. Like if I reduce the test pattern generation time by finding out a good alternative path for propagation etc., it does not hamper your quality of service. But if I somehow reduce the number of test patterns, there can be multiple ways of doing it. One can be by slightly reducing the fault coverage. You can tell that this part of the circuits are not prone to failure, I do not require to test them. So that is one very simple way of reducing number of test patterns to be applied, which you reduce your test application time as well as test pattern generation time, but again to be remembered that that will slightly bring down the quality of service. And again such type of information are not any algorithmic or any kind of algorithmic approach to that. It is statistics and based on the designer feedback which will tell you that this region of the circuit has to be tested well, this region you may drop it, etc., etc. So there is no such algorithm to do that. So in such case we go for optimization, but at the compromise of some kind of a quality of service. Like in case of bridging fault, we should assume, like in Stuckat fault model, we assume that only one Stuckat fault can happen at a time. That is again a slight compromise with the number of quality of service to a very little level, because any two Stuckat fault can happen together. But NC2, NC3, 2 can happen together, 3 Stuckat fault can happen together. But if you take it, the number of all fault combination will be huge. It will be 3 to the power n kind of a stuff, normal Stuckat 1, Stuckat 0. So each line there will be 3 to the power n and it will be exponential blow up of complexity. So here we are assuming a single Stuckat fault model basically, which is nothing but slightly compromising on your test quality solution. Like in bridging fault, basically it can happen that in a region, this is a region, multiple lines are passing together. It can happen that all of the line may get stuck, or any 2 lines may get stuck, any 3 lines may get stuck. So all such combinations you have to study. But that will again blow up the fault model complexity like anything. So people assume that any two lines can be stuck together, and that for that we will be considering as the bridging fault model. So any 2 lines means again we are compromising on the quality to speed up or optimize the test development time as well as the test pattern application time, because the test patterns will be reduced. So ideally, I am saying that all lines may be being a problem, but that will lead to an exponentially high. So as per the fault model, what they take, this is something called a AND OR logic fault model, AND OR bridging fault model. So what they assume that the 2 lines are there, they get coupled. By coupling, the effect is a AND gate or a OR gate. I will give you an example. So let us take a very simple circuit example which we will be using throughout. So these are, now I will be mainly talking about sequential circuit as examples, because we already know the scan chain. So scan chain means you can directly set or reset your flops. So these are simple circuit, the 2 lines. So any 2 lines may have a Stuckat fault, thus any 2 lines may have a bridging fault. So now one thing is there. So generally again one optimization people do, that is actually region of bridging fault. Like for example, this line and this line may not get coupled because they are quite far in the layout. So generally people will try to take a window that maybe only these 2 lines, these lines may have a stuck phase, in this line have a bridging fault because of the coupling, because of the close proximity. Then they will move the moving window. So this way they will have a moving window in the 2D space. So that you can actually find out which are the lines which are in close proximity, only that can have a fault. So NC, even if 2 lines taken together, 2 lines are far apart in the layout, may not have a coupling fault, or in fact they will not have a coupling failure or a bridging fault. So we will optimize on that level, and to my understanding that does not actually lead to much lowering of quality of service, or not even a single percentage of fault will be lost or defect coverage will be lost if you are taking a assumption like only lines in the close proximity will have such kind of coupling. But it can happen that these three lines may get coupled because they are in close proximity, but to avoid complexity people generally try to take only 2 at a time. But now slight advances are also happening in which they will try to restrict the window size, but in that window they will take 3 or 4 or 5 lines in coupling. So there are a lot of optimization techniques in this course, basically as a 20 hours course. So we will try to give the basic philosophy to you. So one way of optimization is that you just take 2 at a time and then have a slightly bigger window size, that is the proximity in which the lines can have a short or coupling. Or in other way what people do, which is not a very well popular approach, but still some people have found out that is giving good solution. They try to keep the proximity window small, and in that they assume that multiple lines, more than 2 lines may get coupled. But anyway, let us come back to our old problem which we are dealing with it. So let us assume that we are going to take E1 and E2, 2 lines which are in close proximity have a bridging fault, that is they may have a coupling. So what is the coupling about? So they assume that these 2 lines E and E2 which are involved in coupling, they have some logical interference, like it's an AND interference. So E1 will be fed to this line as E1 star. Let me zoom this part. So if you look at it, E1 should be initially was feeding to E1 star, this line, and E2 was feeding to E2 star directly. But now due to coupling there will be an AND logic. So E1 and E2 are not independent, but generally what will happen is that the value of E1 and E2 will be ANDed and they will be feeding it to the output. So of course if E1 is equal to 1 and E2 will be equal to 0 or vice versa, there will be basically a failure in the output of the circuit basically. But 0 0 1 1 there will be no effect, because 0 0 means both the output of the AND gate is 0 and vice versa, and for 1 it will be obviously 1. But it is not only about the AND gate, there should be another dual of it. First you should replace by AND gate and then you should replace by OR gate. Anyway, the OR gate will be just same, just in this case you have to replace this OR gate by a AND gate by a OR gate and apply the same principle. So I am not going to discuss it in detail, but that is just the dual of it. That is same redundant. To avoid wastage of time, I am not going to cover the same example with the OR gate. You can try it at home. So there are two parts basically. One is called dominating and one is called getting dominated. All input patterns which result equal to 1, that is E1 equal to 1, sorry E1 equal to 0, E1 equal to 0 is AND gate, so E1 equal to 0, and detect Stuckat fault E2 by propagating to an effect to an output. Now I will give you the philosophy, then we will see the slide. So basically what happens? So when there can be a problem, so there can be a problem if this is a 0 and this is a 1. That is E1 equal to 0, E1 equal to 1. So what should happen? Ideally speaking, here you should be able to propagate 0 and here you should be able to propagate a 1. But now this will not happen because this is an AND gate, so there will be a coupling and E2 will be converted to 0 because it will be pulling it down. So in this case what is happening? We call that E1 is dominating E2, and in the other case when E2 is equal to 0 and E1 equal to 1, we will call E2 is dominating E1. That means obviously whose value gets propagated is the dominating line and whose value gets changed is the line being dominated. So therefore they say that bridging fault testing is very simple, similar to testing of a Stuckat 0 or Stuckat faults, but with a slightly added condition. Like in this case you see, for example, I want to test this bridging fault. So what I have to do? I have to apply any one of these patterns, either 0 1 or 1 0. Because both of them 0 0 1 1 will not have any false sensitization effect. So false sensitization in this case is what? You have to apply a 0 or a 1 or vice versa. Let me just take this pattern. So I apply a 0 over here and I apply a 1 over here. This will sensitize the fault. Because in that case what should happen? Ideally 1 should go over here, now a 0 should go over here. So this is actually a Stuckat 0 fault. So just look at the philosophy. I actually require to test a Stuckat 0 fault at E2. That is what I have to do. And at the same time, I just require another simple condition that E1 should be equal to 0. So basically, bridging fault testing is nothing but a simple Stuckat fault test only, but with a slightly different problem, that some other lines in the context should be having a different value which should be set and reset. For example, let me just assume that we are not going for any kind of a bridging fault test. I am just assuming that this line I am going to test for a Stuckat 0. This is what I am going to do. Just assume. In this case, what is going to happen? I have to justify this line, sensitize this line by 1, and then maybe I have to propagate the value of D over here, and then I have to go for the backtracking, which is actually going to justify all the values. But in that case, I will not bother that whether E1 is a 0 or E1 is a 1. That I don't have to bother, because in ATPG it will just give me any value. But in that case, you have to now think about the optimality. If somehow I could have put a 0 over here, I could have tested the Stuckat 0 fault as well as I would have tested the bridging fault over here. But if I would have put a 1 over here, this is just going to test the Stuckat 0 fault. So basically, testing of a bridging fault is similar to testing of a Stuckat fault model only, but with some added constraint like this. I will make the things more elaborate, so we will understand this. So I just develop the basic philosophy that testing a bridging fault is very similar to testing a Stuckat fault, but with some added constraint in some other lines, so that the bridging, this coupling gets activated. So in the new method of optimization, what people do is that people try to first find out the test patterns for a bridging faults. So when all the bridging faults will be covered, you will find out that a lot of Stuckat faults have already been covered, because bridging fault testing is nothing but Stuckat fault test with some additional constraints in the line. Whichever Stuckat faults will remain, that you can go for the traditional approach and it will be done. So here actually you are getting a very nice solution which people have found out, that optimization is at this level. Do not start at Stuckat fault. You start at the advanced fault model. Of course, you will find out by testing the Stuckat fault in the advanced fault model, lot of Stuckat faults will be by defect covered. Then you just start test for the remaining and you are going to get the solution. Because as I told you, you are not going to touch upon every combination of patterns, every combination of lines in a circuit. Typically, as this is very large, we always restrict the bridging fault to certain regions which may have very compact layout or which we know may be prone to failures. So for certain regions of the circuit, we go for such sophisticated bridging fault test because test generation in the last in Stuckat fault is just to sensitize, propagate and justify, but in case of bridging fault also some additional constraints has to be met. So test generation time is slightly higher. So we restrict the test part to certain parts of the circuit, and then we find out by testing the bridging faults what additional Stuckat faults already covered and for the remaining go. So this is another optimization people try to apply. This is one of the most important optimization rather which people try to do when they are covering the fault models in the modern context. So this is what I am saying, just you can read through the slide. So all the input patterns which result E1 equal to 0, so it is the AND gate. So which line is 0 will try to drive the other gate, so it is basically a dominating line and detect a Stuckat fault in E2 by propagating the effect to the output, and this is the other one, in which case E2 should be dominating and you should propagate the value of E1 to the output. So this Stuckat 0 fault will be de facto tested at both the lines, but only with an additional constraint that in one case E1 should be made 1, in the other case E2 has to be made 1. So this is anyway similar to Stuckat fault, but this is an additional constraint. So if the circuit is very big, you can understand that even adding one more complexity will lead to more amount of time, more amount of iterations, because it is not about just setting another constraint. Setting another constraint means you may have to reiterate, because you may always start having conflicts. More constraints you put, more conflicts you should have, and more iteration on the test pattern generation rounds has to be there. So people try to restrict their bridging fault models to a small part of the circuit. Maybe they assume that there is lot of congestion in the layout over here, and that also they will start making a moving window concept. So this advanced fault models generally are restricted to some specialized zones. Okay. So now let us look at the example we were discussing in a more color animated and a better manner. So as I told you, we are just taking the example that where E1 is having the value of 0, and let me zoom this part. So we are going to try to take this E1 is equal to 0, and D you have to generate the find out that whether E1 is dominating E2, that is it is 1, but actually it is making it 0. So you have to design a Stuckat 0 fault over here. But that means by testing the bridge and bridging fault, because AND bridging fault you have to test vice versa, not only about this one dominating this, also you have to see whether this one is dominating this, both have to be tested. So both way we will be testing the Stuckat 0, one case you will be testing the Stuckat 0 fault at this case, and the other way you will be testing the Stuckat fault at E1. And then again, I am not showing that, again you have to also consider the OR bridging fault. So in that case Stuckat 1 value will be tested, because it is just the dual. You can do that hand calculation at your home and you will be able to find out. But again, as I am telling you, so what is the beauty or what is the optimization over here? That is, first you go for bridging faults, bridging fault test, and you will find out that lot of Stuckat faults already have been covered. Like in this case, you will be finding out that Stuckat 0 faults at both the lines and Stuckat 1 faults at both the lines will be covered when you are considering the AND and the OR bridging fault respectively. But again, problem here is that you have to have an additional constraint, like when you are testing a Stuckat 0 fault at E2, you have to make E1 equal to 0, and similarly when you are going for a Stuckat 0 fault over here, you have to make E2 equal to 0. So this additional constraint means some more justification you have to do in the circuits, and more you try to justify, lot of conflicts may happen, and you may have to reiterate to design the circuits. So in this example I have not shown the iterations, but if you just take a wrong path or you just take wrong values, but I will try to show you the different variations of solutions are possible. By chance if you take a wrong value, you may have to again go for reiteration. That is very important, which you have to understand. That means what? That when you are justifying, many times you get an option either to give a 0 or a 1 at the some line. But if you take the wrong choice by chance, then you may have conflicts. So large circuits, more options will be there and larger conflicts may happen. So more type of constraints like E1 equal to 0 along with the Stuckat 0 fault will lead to more type of constraints, conflicts, and more iterations you may have to do. So that is why bridging fault test pattern generation is a more time complex solution. That is why people optimize by trying to restrict the window size and also the regions. Okay. So these are Stuckat 0 fault. So I have to apply a 0 over here, which is the constraint, additional constraint, and then I go for a propagation. Again, as I told you, as we are having a scan circuit, so in fact I assume that the flops are not there, and I just go for something called a normal ATPG. So normal ATPG means Stuckat 0, I apply a 1 D inverter D prime, that is what I am propagating the value to this, and here I require an additional 0 over here. Now basically I have to try to do a backtrack. So if I try to do a backtrack, let me just look at this picture. So NAND gate I have to put a 1, I can again, this is a 0, so I require 1 over here. So again here I am trying to tell you the options, like it's an OR gate. How can you get an 1? You can get a 1 of 0, 1, 1, 0 and 1, 1. So 3 options are there. So here I have taken explicitly, I have done some calculation and I have taken the option 0, 1. But if you take the 1, 1 as an option, you are going to have conflicts. Like for example, here the requirement is a 1. In this case the requirement is a 1. So it's an AND gate, you can get a 1 by 0, 0, 1, 0 and 0, 1. So any of the 3 options should do. But by chance if you take a wrong option, then you are gone. Basically you see, I can have a, let me just say, just give you, so you can also have a 0 over here. It's possible because 0, 0 is also going to give you a 1. And as I told you, you can also have a 1, as I have told you, it's possible because 1, 0, 1, 1, 0, 1 both can give a 1 at the output of the OR gate, that is at E2. But now if you take a 1 over here and a 0 over here, as this is the same line, there will be a conflict. So there will be a issue. So you can see there are a lot of conflicts over here, and in fact, so then you have to again reiterate. So this is standard reiteration. So for example, say I am intelligent and I am putting 1 and over 1, so no conflict is there. But you can just see that I have to again go for another kind of a justification over here. So there is a new justification required over here. Sorry, another constraint like E1 equal to 0 you have to put explicitly, because it is not a Stuckat fault test, it is basically a bridging fault test. So for example, I am putting a 0 over here. But as I know that to put a 0 at the OR gate output, you require a 0 over here and 0 over here. Now, as you can see that this is a NOR gate. So NOR gate output 0 means basically you can have the solution 0, 0, 1, 0 or 1, 1. So whatever may be the case. So for example, basically if I have the answer here as a accepting 0, 0 at this position, it should not be 0, 0. This is not allowed. Unless all other cases like 1, 0, 0, 0, 1, 1, you can also have the value of 0 at the output. So if I, for example, this is also going to hold and this is also going to be a valid solution to get a 0 over here. But if you see, if I make a solution like this, so this line is basically connected to this line and there can be a conflict. So therefore what I am saying, trying to emphasize on this point is that, so more number of constraints you have and more bigger the circuit is, there are a lot of options, like here I am getting 3 options, here I am getting 3 options, here also I am getting 3 options. So if you are not taking a good option, you can always have more number of conflicts and will be having a reiteration. So that what it tells that, so even just testing a Stuckat fault means just you have to have a constraints on this part of the circuit. But as it's a bridging fault, also you have to consider some additional part of the circuit where some constraints has to be applied. So more number of conflicts can happen and test generation time will be higher. So that is why for optimization reason, again I am repeating, they try to restrict it. But the advantage part of this advanced fault model is that if you test the bridging fault, automatically some Stuckat faults will be tested. Anyway, let us come back. So basically I am going for this level of justification, and then again additionally I should have a 0 over here. So had it been the simple Stuckat 0 fault, this would have been done the job. So now basically if you look at it, so I require basically some kind of values like, let me be more precise and look at the exact values. So if you see, I say that I require a 1 over here and I require a 0 over here. So if you can find out this 1, basically this line is actually fed back from this flop, from the flop number 2, I require a 1. So again I assume that they are all scan flops, so I will basically make this line as a 1, and if you can look at it, to justify this line basically, if you look at the output of the second one, so it is actually coming over here, the output of this one is coming, input of this AND gate at E2, so basically I require a 0 over here. So as how do I do this? Basically as all these flip flops are scan flops, so I can just disconnect these two and basically I can make them 1 and 0 by the scan manner, and then I can go for this approach. So basically, so directly the flip flops are controllable, that is what I have assumed. So basically this is what I propagate the value over here, and this is basically the requirements over here. Additional constraint is something like this. Then for the AND gate I require 2 zeros. So basically this is one AND gate. To make the output of this AND gate output 0, I can just put a 0 over here, my job will be done. And similarly you can find out from the figure, let me just clean it up, that very easily you can propagate and justify. Again just re-emphasizing slightly that this additional stuff will require additional amount, may require additional amount of iterations, because more number of choices will be there, and if you are taking a wrong choice, conflicts may happen. Let me do it in steps. So the ATPG tells that basically I require a 0 over here and a 1 over here. So I have to set this flip flop, set and reset. So first step what you do basically is that you decouple the flops, and basically this has to be set by the scan. Next state is basically the flops are already set, and basically then you again reconnect the flops to a normal mode, and then this is the test pattern. Input will be, primary input will be 0, that you already have found. You can go through the slide in detail and you will be able to find out. Then what is going to happen is that all the red marks signals will be validated. D bar will be appearing over here, that is normal 0, faulty 1 will be the case. And basically, so if there is this Stuckat 0 fault over here, rather in this case I should not call it a Stuckat 0 fault over here, because I am restricted this line to 0. So if there is a bridging fault over here, you are going to get the answer 0 over here, else the answer is a 1 over here. So in fact, bridging fault is testing a Stuckat fault with some additional constraint in some other lines. That is what is the idea. Then basically I am applying this fault, that is sensitize, propagate and justify, all these things are done, and basically then you apply a clock. So now the flip flops are already connected, the value is applying over here, you apply a clock pulse, and the value will be, D prime will be latched over there. So the D prime is latched over here. Now again I have to cut out these flops, because otherwise how do I get the values of these flops? Flip flop value which has been, fault value which has been latched over here, how do I get it out? I again make a scan connect, and then I will actually propagate this value out of the scan chain. That is D prime will be output, and I can just find out that there is no OR bridging fault over here, or if the OR bridging fault, sorry, AND bridging fault is present or not, I can detect, in which case E1 is dominating the line E2. Similarly, you have to repeat it for E2 dominating E1, which will be just the dual of it. In this case, the fault propagation etc. will be having over here, and here you have to, sorry, this next case basically will just reverse it out. In the case next case you will just reverse out. So in this case here you are going to have a Stuckat 0 fault over here, you have to make this line explicitly 0, and the whole process will repeat. So two steps you have to do, which are actually explicitly mentioned over this figure. This figure already we have seen, we have just made a 0 over here, explicit additional constraints, and then find out Stuckat 0. Similarly other way you have to make it a 0 over here, and you have to find out the Stuckat 0 fault over here, which is just the mirror image of this. And then again the other way you have to do, you have to assume that there is a OR gate over here, and you have to just make the dual of it. So in this case you will be assuming at the Stuckat 1 fault over here, and here you have to explicitly have the value 1. So that is a dual you can easily calculate. So basically what happens, you can observe, again I am repeating the key terms here, that if you go for testing the bridging faults, automatically you will find out that a lot of Stuckat faults are already getting covered. So what we do basically, we find out patterns and test for the bridging faults, then automatically whichever Stuckat faults will be remaining, we can go for the normal ATPG for the Stuckat faults. So that is a byproduct basically. So you can, but you can easily find out by an intuition, if I go for bridging fault test on the entire circuit, Stuckat faults will automatically get covered. But in fact that test pattern generation time in such a case will be large, and in fact that is not required also, because not all parts of the circuits are generally highly congested. You can pinpoint that which are the regions of the circuit highly congested, and which case required to have a bridging fault, where you need to do a Stuckat fault test etc. So that way the optimization happens in such a way, we go for the majority important regions, go for bridging faults, automatically some Stuckat faults will be tested, and the remaining ones we can go for the ATPG method for Stuckat faults. But one interesting fact is that some people also try to find out in this manner, that if I go for only Stuckat fault testing, say for example, if I go for a Stuckat fault test over here, but some pattern will be applied over here. Of course, this is for me this region is X. In this case, I don't bother what is happening to the circuit. But by chance, it may happen that this line basically has a 0, or as you are not bothered about it, it may be either 0 or a 1. So by chance if it is a 0, so bridging fault is default tested with a Stuckat 0 fault over here. But in fact if it is not, it is 1, then only the Stuckat 0 fault over here. So the test pattern basically which is resulting in a 1 over here and testing a Stuckat 0 fault over here is called a bad test pattern, or not a very good test pattern, because it is only testing a Stuckat 0 fault over here. But the test pattern which is having a 0 over here and testing the Stuckat 0 fault over here, we will call it as a good quality test pattern, because it is actually testing both of them. So our main goal in advanced level of testing is to find out good quality test pattern, so that it covers multiple faults at a single go, or not only multiple faults of advanced types in a single go. So basically what, as I was saying, what are the basically optimizations people do? They generally consider only 2 lines at a time, and that also line to close proximity, because otherwise if you are taking all combinations of faults, NC2 will be a very large number. So basically what you do, you actually first test for bridging fault, automatically it will cover large number of Stuckat faults. So basically for large system or complex systems, what we do, we cannot have a bridging fault for the entire part of the circuit. We take some complex part or which the designer tells are more complicated, has to be looked into. So we are going for restricted search in that case, and remaining for we go for a Stuckat fault models to be covered. So but this is, you cannot assume that this is a white case or a Bible kind of rules for all kind of test circuits or test industry. People have their different rules, and where people solve it is also a very secret for that industry, that will not reveal it to everybody. But this is something called some kind of golden rules which people try to apply, that taking only 2 lines, restricted to regions. Basically you go for bridging for certain regions, and for Stuckat faults you will going for the other. But I cannot say that some vendors who, in which case these circuits are highly compact in nature, they may want to apply bridging faults for the entire part of the circuit. In that case testing of the Stuckat faults is de facto done. So this is not a very golden or Bible kind of rules, but these are basically some kind of thumb rule. As I tell you, generally we say that 2 lines are considered. But for many cases people take smaller windows, but in the smaller windows basically they take more number of lines, they assume to be having a coupling fault. So that way. So another very important fault model is a delay fault model. So what is a delay fault model? Because nowadays circuits are operating at a gigahertz level. So you should know that not only the circuit is operating properly, there does not have any coupling fault, there does not have any Stuckat fault, but the answer should come in a predefined amount of time. The AND gate should compute the value 0 0 to 0 or 1 1 to 1 and so forth for all the gates in a predefined amount of time. That is, the delay from one end to the other end of the circuit should happen so that it can make the speed requirements. So delay fault model is a very important fault model for most kind of modern circuits. So almost all circuits nowadays also cover delay fault test. But as we will slightly see that now, the delay fault generation is also complicated, as well as the fault application requires a very high cost AT, because here the patterns have to be applied at the gigahertz level. Because if I am going for a fault, means what I am saying, if you are going for a delay fault test, that is you are applying some patterns and then you apply the next pattern, and you should know that the AND gate is computing the results at the near accurate time. So in that case obviously test pattern has to be applied at a very fast rate, and also the data has to be latched at a very fast rate at the gigahertz level, which is typically the operating range of the circuit. If you are not able to do that, then basically delay fault test has no meaning. So therefore AT is a very costly in such cases, and people actually nowadays apply for what do I call design for testability methods, that they do not exactly require an external equipment to do this, they put some internal circuits to apply those test patterns, which we will be looking at into the next few lectures, which we call design for testability optimization. But for today's class basically we will try to see what the fault model is, what has to be applied and what is expected. So we say that the input output of a gate may have a delay to rise or delay to fall. Basically all gates will be having this or this, rise or fall, that is what is required, and you should be able to do it in the at speed requirement. If you are able to do that and there is no stuck or bridging fault, basically the logically it is proper and there is no up and down for such cases, everything is in time, then you can know that the circuit is having proper functionality, and also it will be able to meet your speed requirements. So the magnitude of delay caused by delay fault is such that the new signal value at the output of the next function block corresponding to the transition of the gate under fault is not latched by the trace register. That means what? Generally we have a flip flop here. We have lot of combinational circuits over here, we have another combinational circuit over here. The magnitude of delay fault such that the new signal, this is actually called the NSF, we may call it next state function block or some combinational block. So you apply some inputs over here. Then basically this is your clock, this is your clock. So basically before they arrive, so some patterns come say at this clock edge, some input patterns come over here. Then this NSF block or the combination cloud will compute the values. But before the arrival of the next clock pulse, this data should be available over here before the setup time of the flip flop, so that the exact value can be latched. If you are not able to do that, that means there is a delay failure in some gates or some parts of the next state function block. So that is actually a delay fault. We will take an example. So this is an example of a circuit. We are assuming lot of examples can be provided, but I am mainly in this course we are trying to give you the basic philosophy. References will be provided in the course material or the course pages in the site. You can easily read for the advanced part, because this is course which is slightly requires some advances which were basically made into practice to tackle modern day circuits and the modern day failures. So we will try to give you an idea of the main clause, basically the crux of the how to do it, and the other parts you can very easily read and you can even do it. So here we are going to talk about delay to rise. Delay to fall will just be the mirror image of it. So what happens? Delay to rise means, and we are assuming that only in this line, because we have to in fact try this delay to rise and fall, we have to do it for all the gates. So we are assuming for gate 1 there is a delay to rise fall. That means whenever you change the input such that the output of the gate should change from 0 to 1, it is not happening in this proper time, they is slightly delayed and it happens over here. So this is basically a delay fault model or delay to rise fault. Delay to fault model will be very similar, just the reverse of it. So we have to verify this. So of course very basic philosophy we have learned about around 2 to 3 hours of lecture in test till now. So and from the intuition also you should have some, you should apply first a 0 over here, and after some time you should be able to apply a 1 over here. That is the sensitization part, and of course the value has to be propagated to the output, so it has to be latched. That means, but the change from 0 to 1 at this has to be done in a very fast manner. So first test pattern should be such that a 0 is applied over here. Very quickly you have to give another test pattern, so it should become a 1, and that should happen in a quick amount of time or reasonable amount of time by gate number 1, because we are assuming the single fault model in all cases. By the way, most of the fault models assume a single fault. That means only in this in out line we are having a delay fault. So if there is not a delay, the value will be propagated over here and you are able to capture the value in the right manner in the flop. Otherwise there is a delay fault which can be captured. So 0, and immediately you have to make it a 1. So first I have to make the value at this line as a 0. So how can I do it? This is an AND gate. So NAND gate output is 0 only if everything is a 1, 1 and a 1. So you can see A and 1 are primary inputs which I can easily make 1, but the H, which is the feedback of this flop, also has to be made 1. So what I have to do is that I am first going for the ATPG. So I know that this is what is the first pattern to be applied, and for that basically I require the flip flop to be having a value 1, which I can easily do by a scan chain. So which I cut the value, cut the flop by a scan, and then by the scan chain I actually make the value 1 and apply 1, 1 and 1. So of course NAND gate 1, 1 and a 1 is basically a 0 over here. Now again I couple the flop with the circuit, and then what I do in this is the first case 1, 1 flop scan chain, and this is a 0, so 0 is over here. Then what I do basically, I reconnect the flop, then I actually make what actually they call it test for Stuckat 0, because obviously we are going to test for this. So first you make this 0 and then you apply a 1, and this 1 should propagate properly. That means what? You are testing a Stuckat 0 fault but at speed. That is what is very important. We are testing a Stuckat 0 fault at the line but at a very, very high speed. So what I do at this clock edge, at one clock edge I will make the line A equal to 0, from 1 to 0. In fact you can also do same for B. So if you do this, after a certain amount of delay, the in will become a 1, because an AND gate, so 1 0 1 0 0 1 whatever, if any one of the line is a 0, so the AND gate will give the answer as a 1. So there should be a rise. But if this is so much delayed, that means this is a Stuckat fault. So if the rise happens and in proper time, then the value will be propagated to the basically flop and it will be captured. But if it cannot rise, that means there is slightly delay, then what is going to happen? This one, it will happen. It is not that the line is stuck. This line is not permanently stuck. It will rise, but the rise time will be so high that basically it will not be last in the second clock period. It will be lost. It will be last in the third clock pulse or even less, even later. So in fact, for that case, basically it will assume that this is a Stuckat 0. The rise has happened, but it is so delayed that it cannot be latched by the flip flop. So basically it is nothing but a Stuckat 0 fault. So what I have to do? Stuckat 0 fault means I have to apply a 1, so which I can do by having A equal to 0, B equal to 1 and H equal to 1. So this is D. I am assuming this line I will be propagating the value. So inversion will be D prime and again another inversion will be D. So basically what is the answer? This is 1 in normal and fault in 0. This is what is to be expected. Now this scan chain is disabled. I am making A equal to 0, but I am doing it extremely fast. That is from 1 to 0, this A I am doing at the level of gigs. So that is why I require a very fast ATE to do that. So in fact, an external tester having such high frequency is very expensive. So what we try to do, many times we put the built-in self-set circuit inside the circuit itself, which we are calling BIST architecture, that will actually give the impulse, which we will see later. For the time being, let us assume that such a fast signal can be given, but assume that, or you should also know that applying such a fast signal is from an ATE, the ATE cost is very high. So we do that. So what basically, let me just remove the writers from the slide so that it becomes clear. So that is what is the case, and basically at this clock edge all this stuff is happening at this clock age. Next, what happens? If everything is proper, by the next clock age, you are going to get the value of a 1. It is very fast, so it will go from 0 to 1. From here, it will be falling from 1 to 0, and again, basically, it should come over here, and in fact, basically, you should get this rise over here. So, in fact, in the second clock age, so basically, if it's an AND gate, I should get a 1 over here. So, in fact, slightly I should backtrack over here. So, this is the value is propagated. To be justified, I require a value of 1 over here. To require a value of 1 over here, I cannot have a 1 over here, because that will create a problem. In fact, I should make the justification I forgot to do. So, just make it a justify. You make the value of 0 before an AND gate. So, it will be 1. So, in fact, I should say that in fact B should be equal to 0. In fact, B was, if you make B equal to 1, there will be a conflict basically. So, I make B equal to 1. So, basically this answer is a 1, and so it is a proper solution. So, this case is 0, then actually I have to make A equal to B equal to 0, then I have to connect. But in fact, this B may not be at speed. That is what is the idea, because generally when I am testing for the propagation of this path, the B is from 1 to 0 again, this can be made in a slow pattern. Mainly I am trying to hit this circuit on this part, because I am assuming that this is what is the path being followed for the at speed testing. So, anyway, so this line is for just for justification, and the line A, in, out, E and G is for propagation and sensitization. Do it so that I get a 0 over here and the value is a 1 over here. So, basically what happens? So, in this case, so this rise should happen, and this should happen before the arrival, that this is the duration. This is duration. So, this change actually should happen just after this, because this point is triggering it, and basically I am sorry, I should say that this is actually the trigger point. So, this is basically the trigger point. So, this is the trigger point, and this change is where the delay is being targeted. So, this should happen so fast that all these things should happen before the arrival of this clock pulse. So, if the clock, before the arrival of the clock pulse, everything is in proper, then you are going to get the value of D over here, and that will be actually latched by the flip flop over here. That means at this clock age, that means the value of normal it is 1, failure it is 0. So, if D is appearing and if it is a 1, that rise has happened and it has been latched by the second edge, that means this path, this fault, in this path in fact actually has a no delay in doing it. In fact, you can also find out that if this is true, then this is also having no fault and this is also having no fault. That means the gate E does not have a delay to fall fault, and again the gate 4 does not have a delay to rise fault. So, by this pattern, many faults, delay to rise and fall faults, delay to fall faults have been detected. Basically, this fault, this delay to rise, delay to fall, delay to rise could be easily detected by this pattern. But in fact, anyway, we are just highlighting on this, so let us look at it. So, basically what happens, this is not a Stuckat fault. In fact, basically what is going to happen here is that after a certain amount of delay, basically, even if the delay fault is there, it will rise, but it will rise much after this one. So, in fact, this will assume that there is a Stuckat fault. So, basically rise will be there, but still the D flip flop will assume to be a Stuckat fault, because it only latches value at the clock edges, and in fact that is required because all computations should have to happen between two clock edges. So, in fact, what is the delay fault model? It is very similar to testing of a Stuckat fault model or a bridging fault model, in which case you should have, in the fault path, you have to give a sensitization. Sensitization is nothing but you have to first delay to rise means you have to apply a 0, and next part you have to make a 1. But that 1 has to be done basically in a very fast manner at the level of speed, and then you have to latch at the value at the flip flop also at the same speed. But anyway, that is not a problem because that is the normal part of the circuit. So, it will be generally operating at the gigahertz level. Only problem is that this has to be applied at a very fast rate. That is why ATE cost becomes high and so forth. So, if you are able to latch it at the value at the output, there is no delay fault for rise delay fault, otherwise there will be a delay fault. So, you can also see over here that if you are going for delay fault model, lot of Stuckat 0 and Stuckat faults will be by de facto covered. So, that this is the other part of it. So, basically the value of D was latched and you are putting it to the scan out, which you can again do at a slower pace. So, only problem is that the application of test pattern as the input at a very fast rate, but all others like the D frontier you are taking out to the scan can be very slow approach. So, only this is where the cost comes. But anyway, we are talking about the optimization. So basically what, here also you have see the beauty that we are going for the testing of a bridging fault, whether you are testing for a delay fault, basically Stuckat faults automatically starts getting covered. But not the other way, that if you are doing only test for cover for a Stuckat fault, bridging fault may be covered or may not be covered. Delay fault will not be covered because you are not applying test pattern at speed. But if you are going for the advanced fault model tests which are required for modern day circuits because they are manufactured in this submicron level, the Stuckat faults automatically start getting covered. But what is the optimization for delay faults? Because optimization at the bridging faults already we have seen, restricting the line, restricting the regions. But here we are not, in case of delay fault, you understand that it is a very costly affair because patterns have to be applied at speed. So what we do? Basically we try to apply test pattern only in critical paths. Critical path means the longest path. If you look at this circuit, this is the path which is the longest path, means more number of gates are involved. This is the path which is slightly shorter. So if this gate has certain delay, it is not that much of a concern because generally speaking the delay of this gate will not be such high that we will undertake all the delays of the gates and still it will be more higher with a fault. That means if there is a delay fault here, delay fault here, delay fault here or here, we will be more concerned because the path is long. It may easily violate the timings. But this gate can have a delay fault, but the delay will not be so high that will actually take up all the long path delays into account. So generally we try to find out something called the critical paths which are the longest path, and then we try to see whether the delay faults are happening there or not. So this is again an optimization, because if you are trying to take all paths, it is neither required, because I told you in this example whatever fault might be there in this path, in this gate, as this path is shorter, it cannot be higher than all the gates taken together in the other path. So we take only the longest path which the designer will tell you as the most critical paths or near critical paths. On those we will go for the delay fault test, so that your test time and your test cost also remains lower, because delay fault test is expensive, because the ATE has to apply faults at very fast rate, patterns at very fast rate. So we restrict it to very specialized regions of the circuit where you know that if the delay increases, the latching of data from this flop to this flop may be delayed or may be hampered, and so our staff wheel has to be organized in this manner. So that is why the optimization is that we do only for critical paths, because ATE cost is very high. And of course, as you have seen that only testing of the delay faults will easily cover Stuckat faults. So what we have seen in this? So we have basically seen that advanced fault models are very much required if you are going for testing of circuits at deep submicron level, which is the de facto standard of fabrication for NOCs and SOCs. Interestingly, if you go for testing of the advanced fault models, automatically some Stuckat faults will be tested. What remains to be done? You go for the remaining at the later phase, and so that you go for a 100% coverage. So this idea, go for advanced fault model test in a restricted manner and an optimized manner, so that you do not overspend on testing, and then find out by de facto what are the Stuckat faults automatically getting tested, and remaining one you do. So this is how basically the modern test pattern generation optimization happens, by finding out good quality test patterns. In fact, every test pattern, whether it is a stuck fault, delay faults, etc., nothing but these some input patterns at some speed. So among this set, which are the good ones? The good ones are those which will cover multiple different type of faults. So such patterns has to be selected, and in this lecture basically we have tried to give you an idea on this. This is actually a very new research area, that how such important fault models can be covered, how they can be optimized. We have given an idea of the very basic and how people start about. So in the references we will try to give you more ideas on that, which you can read through and get more advanced how people are dealing in the modern days. In the next lecture basically we will be trying to look at some aspect of test pattern type of compression, that if you have a huge data, how can you compress it and try to make the test data size limited. And then we will go for see how additional structures can be put in the circuit, so that the test time and test optimization can be developed. Thank you.